Hello, my name is Eric Cinnamon. My final project for analog electronics was to design and build a circuit that controls both the speed and direction of a DC motor. I'll start by showing the schematic here. So this is called an H-bridge, where four transistors are used as switches to control the direction the current flows through a load here. These BJTs operate in either the cutoff or saturation region, dependent on whether or not the voltage difference between the base and the emitter, or VBE, is higher than the threshold voltage. If the BJT is in cutoff mode, then the current will not be able to flow from the collector to the emitter, and the transistor is considered to be off. But if the BJT is in the saturation region, then the current can flow through these 2 points and is considered to be on. For the PNP transistors on the top here, this means that for them to be on, they must be grounded, and for them to be off, we must hook them up to power. But for the NPN transistors, or for them to be on, VBE must be greater than the threshold voltage. So if they are grounded, then they will be turned off, and if they're hooked up to the voltage, then they will be turned on. Now for this circuit to work, for the motor to spin forward, you need a positive voltage on one side and negative voltage on the other. And to do that, you turn on this transistor, and turn off this transistor and this transistor. Since this is a PNP transistor, you will hook it up to ground, which will also hook this NPN transistor up to ground. So this one will be on and this one will be off. For these two, you want this one to be off, so you need to hook it up to power. Since this is an NPN transistor, it is hooked up to power, so it will be on. Now if we run the circuit simulation, we will see from these values over here that from this voltage, which is between V1 and V2, there is a positive voltage across the load, or the motor is going to spin forward. You can also see that the current from the collector of Q4 is a negative 0.6 amps, or 600 milliamps, and for Q1 it is also 600 milliamps, so the current is flowing through this transistor, through the load, and out through this transistor down to ground. You can also see that for Q2 and Q3, there's a very negligible current going through those two. Now if we were to hook it up in the other direction, where we have the two transistors on the left hooked up to power, that means that this PNP transistor will be turned off, and this NPN transistor will be turned on. If you hook the two on the right up to ground, then this transistor will be turned off, and this transistor will be turned on. And as you can see from running the simulation, that we now have a negative voltage across the road, so that our motor will spin in reverse, and also that through Q2 and Q3, we have again 600 milliamps going through both, and through Q1 and Q4, we have a very low current going through them. The reason these resistors are in here is to lower the current going into the base. Now, if we were to add a meter over here and check the current, say this transistor here, and run the simulation again, we would say that it is drawn about 8 milliamps. Now, if we were to remove this resistor and then run the simulation, we would see that the base is trying to draw 4 amps, which is quite a lot of current, and the transistor will more than likely not be able to handle that. So although those resistors lower the gain of these transistors, the motor will have a smaller voltage across it and not be able to spin as fast, but it will save the transistors from burning up. So here we have our final circuit, where we have our PNP transistors here and our NPN transistors here. These are the switches that control whether or not they are supplied power or ground. These two correspond to this side, and these two correspond to this side, where this one will supply a voltage to the base, and these two will supply a ground to the base. This one will supply ground to these bases, and this one will supply a voltage to these bases. Now here we have our 9-volt battery, which is what powers the circuit, and if we measure the voltage across it, we will see that it is not fully charged, but is only at about 7 volts rather than 9 volts. Now if we connect this up, and then we flick on the switches, the motor will turn on. We can then use a potentiometer to change the voltage going to the motor and change the speed. Now if we are to turn on these two switches, we will turn on the motor in the opposite direction and use a potentiometer to change the speed. You can somewhat hear it changing, but it's a bit difficult to tell just on the video, and also that the direction is a different direction. Now if we are to turn this back on, we can use our DMM to measure the voltages across the various transistors. Across the first PNP, we will see we have about 2 volts across it. Across this NPN, we will see that there is about 500 millivolts. Across the second PNP, which should be very similar to the first NPN of low voltage of about 50 millivolts, and across the second PNP, or NPN, which should be similar to the first PNP, we should be seeing about 2 volts, or 2.5. And now if we are to measure the voltage across the motor while it is on, we should see the same 2 volts. This shows that these two transistors here are on, allowing the current to flow from this emitter to that collector, into the motor, out of the motor, from this collector to that emitter, and then back to ground. And if we turn it on in the other direction, we will see that these two transistors now have a lower voltage, and these two are now at a higher voltage, allowing the current to flow in the opposite direction. So this one is at about 60 millivolts. This one should be around 2 volts. This one should also be around 2 volts. If we can get the probes on the leads, yes. And then this one should be at about the 600 millivolt range. And across the motor, we should have somewhere around 2 volts. Or minus 2 volts, and it's been in the opposite direction.